Good afternoon everybody. Today I am going to tell you about the entropy change on mixing of ideal gases. Previously I have told you about the entropy change of a reversible process, entropy change of irreversible process, entropy change for an ideal gas during various processes like the isothermal process, isobaric process, isochoric process and an adiabatic process. So let's start today with the entropy change on mixing of ideal gas. Let us consider two ideal gases, gas number 1 and gas number 2, having N1 moles of gas 1 and N2 moles of gas 2, maintained at an initial pressure of P1 naught and P2 naught. Suppose we mix them at constant temperature. Isothermal mixing is taking place between ideal gas 1 and ideal gas 2, and let the partial pressures of the two gases after mixing be P1 and P2. So the total pressure, let it be P, which will be equal to P1 and P2, and let the mole fraction be X1 and X2, X1 for ideal gas number 1 after mixing and X2 be for ideal gas number 2 after mixing. So we all know the formula for an ideal gas, the entropy change for an ideal gas. It is delta S. Delta S is change in the entropy. Delta S is equal to N. N is the number of moles and R we all know is gas constant. Log naturals, pressure initial divided by pressure final. So this is the formula for calculating entropy change for an ideal gas. Delta S is equal to NR log naturals P initial upon P final, means the initial pressure upon the final pressure. So this is the formula for the entropy change. And from this formula only we will calculate the entropy change for the gas number 1 and entropy change for gas number 2, and what will be the entropy change on mixing the two ideal gases. So for gas number 1, the entropy change, that will be delta S1. So it will be delta S1 is equal to N1 because it was N1 moles. So N1 R again a gas constant, log naturals P1 naught. This was the initial pressure. So the initial pressure is in the numerator, and the final pressure which comes out to be P1 for gas number 1. This is the partial pressure, but here it is the initial pressure. So it will be P1. Let it be equation number 2. Similarly, for gas number 2, let it be delta S2. The entropy change, let it be delta S2. So it will be equal to N2 because N2 was the number of moles of ideal gas number 2, and R is again a gas constant, log naturals P2 naught. This is the initial pressure. We took it here and divided by the final pressure, which is actually P2. So when we mix these both these gases and during at isothermal conditions, means the temperature is kept constant, we have delta S1 plus delta S2. The final mixing will be delta S1 plus delta S2. Here we are having equation number 1 as delta S1 and equation number 2 as delta S2. So delta S1 and delta S2, the sum of these will be simply the addition of these two equations, which is N1R log natural P1 naught upon P1 plus N2R log naturals P2 naught upon P2. Now we will do the further calculations regarding the mixing of the ideal gases. This is the formula for the entropy change on mixing of ideal gas. Equation number 3 we will just now see. So we know that if the final pressure is P, then the final pressure will be equal to P1 plus P2, and according to the Darcy's law of pressure, partial pressure, if X1 and X2 are the mole fractions, then P1 will be equal to X1P, the total pressure, and P2 will be equal to X2P, the total pressure. Now let us substitute these values of P1 and P2 in equation number 3. What we get is N1R log natural P1 naught upon X1P plus N2R log natural P2 naught upon X2. This we have arrived from equation 3 by substituting the values of P1 and P2 from these two equations. We get this. Let it be equation number 4. Now let us consider the simplest case. The simplest case in which the initial pressure of both the gases are same. That is P1 naught is equal to P2 naught, and let the volume of this mixture V be equal to V1 plus V2. So the final pressure of the mixture will nearly be the same as the initial pressure, that will be equal to P naught. P2 naught will be equal to P. Now when we consider this condition and we apply it on equation number 4, this means that P1 naught is actually equal to P. So this thing will get cancelled and what is remaining is N1 R log natural 1 upon x1. Similarly, here also, since P2 naught is equal to P, this is the most simplified case. So this will, what will be remaining here? N2 R log natural 1 upon x2. So we can write it in this form as equation number 5 I have written. What? This 1 upon x1 we can take it as minus log natural x1. So it will become minus N1 R log natural x1 plus, again here it is log natural 1 upon x2. So it will be in the negative form. So it will become minus N2 R log natural x2. So this will be our equation number 5. A slight of rearrangement over here, and what we get, this we see that R is common in both these factors. So this will become minus R we have taken out of the bracket as it is common. So it will become minus R. Inside the bracket we are having N1 log natural x1 plus N2 log natural x1. Since we have taken minus over here, so there is no need of keeping the minus here, it will be here, and since it is inside the bracket. This is equation number 6. So here we are taking only two gases, gas number 1 and gas number 2, and thereby N1 moles and N2 moles. Suppose we are taking I number of gases, not only two gases, but there are I number of gases. In that case, the entropy change on mixing can be generalized in this way: minus R summation of the all the moles of I number of gases into log natural xi. So in this way we have equation number 7, and this is a general equation for entropy change on mixing of I number of gases, in which there are I number of moles. Now let us take a special case in which the total moles of the mixture is 1. Means the mixture is composed, the total moles in that mixture is only 1. The gases are having fractions of it, and for 1 mole of mixture we are having. So in this case, we have to divide it by N1 plus N2, means the total number of moles. Suppose there are two gases, and N1 and N2 are the number of moles of one gas, and N2 is the number of moles of the second number of gas. Then the total number of moles will be N1 plus N2, and what will the mole fraction for number one gas will be N1 upon N1 plus N2. Similarly, for gas number 2, it will be N2 upon N1 plus N2. So we have taken that here, and now consider equation number 6. And equation number 6 is minus R N1 log natural x1 plus N log natural x2. This is our equation number 6. Now when we consider it for 1 mole of the mixture, then the mole fraction of this one, this will be minus R N1 upon N1 plus N2 log natural x1 plus N2 upon again N1 plus N2, since N1 plus N2 is the total number of moles, so log natural x2. Let it be equation number 8. Now, as we all know that mole fraction, we have described it here also, that the mole fraction is denoted by x1, and x1 is equal to N1 upon N1 plus N2. So here delta S of mixture will be equal to minus R N1 upon N1 plus N2 will be x1 log natural x1 plus this is again x2, the mole fraction of gas number 2, and log natural x2. This is equation number 9. So in fact, this is the equation for entropy change on mixing of two ideal gases. Suppose there are I number of ideal gases, means there are several gases which are being mixed, and the whole makes 1 mole. Then what will be the general equation for such a mixture? That will be minus R summation of all the mole fractions of I number of gases and log natural xi. So this will give the general equation for entropy change on mixing of I number of ideal gases. Now we can see equation number 10 is a general equation. Similarly, equation number 7 has also moles of gas number 1 and gas number 2, then you can simply substitute the values in equation number A, and the entropy change on mixing of the gases can be calculated very easily. We can see from these two general equations, equation number 7 and equation number 10, we see that there is no temperature symbol. This means that it is independent of temperature. We have taken the isothermal conditions, and the final formula which we have arrived at for calculation of the entropy change on mixing of the gases is independent of temperature. Moreover, we see that this factor xi is always less than 1. Xi is always less than 1. So when xi is always less than 1, then this factor will become negative. And when this is negative, this means delta S negative, and negative will always be positive. Means that the entropy change on mixing of ideal gases is always positive. Means it always increases. That's all.